Today I'd like to look at a mathematical object called relations. So let's start with an intuitive idea of what we mean, and then we'll go into a technical definition. So relations, we normally write something that looks like this, x, s, y. S is representing some sort of relationship between x and y. So we could say x, s, y means, so if and only if, x and y are sisters. Okay, so S is describing how x and y are related. Another example could be x, m, y. Right, so maybe that means x is y's mother. So what we can see here are two relations, relating objects. Now notice in the second one, order is very important, okay? Because if I say x, m, y, I'm saying x is y's mother. That's not the same thing as y, m, x. Whereas in the second one, or in the first one, the order really isn't important. Because if x and y are sisters, then x, s, y works, but if I changed it to y, s, x, I would still have x and y are sisters. Okay, so this is the intuitive idea of relations. Now with math, typically, right, we're going to use numbers or mathematical objects. We're not going to use people and relationships. So let's get a technical definition and some mathematical examples of relations. The definition is actually quite straightforward, okay? So we can say if some relation R, this is a set R, is a subset of A cross B, then R is a relation from A to B. It's that easy. If you don't remember what that A cross B means, you'll want to review Cartesian product of sets. Okay. All right. So what we're seeing here is that R, to be a relation, just has to be a subset of A cross B. What did the elements of A cross B look like? Those are ordered pairs. So that means our relations can be written as ordered pairs. So I can write ordered pair AB as an element of R, but mathematicians can be lazy and like to put stuff in the quickest way possible. And also it just is useful to write it like I did with the sister and mother examples. So we say ARB. Okay, so order is important. That entry coming in first is the first coordinate of my ordered pair, and that's coming from the first set of my Cartesian product. Typically, we look at relations where the first and second set are the same. So if that happens, so we can say if R is a subset of A cross A, or you could say A squared, then R is a relation on A. That's what we're mostly going to focus on, okay? Because we're heading towards equivalence relations, and equivalence relations will need us to be in that type. So let's get some mathematical examples. Call this example 1. We're going to let a set T be the set of ordered pairs xy, and let's let those come from the integers crossed with themselves, so z squared. We're going to let that be such that x equals the absolute value of y. Using our other notation, we could write this as x, t, y, if and only if x equals the absolute value of y. Same thing. Both those mean the same thing. The first one is specifying my universe. If I write the second one, I have to go back and specify that, okay, what my universe is. But I'm dealing with just integers here. So, I don't know, a couple sample things that would be in this. We could say, what? 0, 0. 0 is related to 0, right? Because 0 equals the absolute value of 0. 3 is going to be related to -3, okay? Because 3 equals the absolute value of -3. So that's how our relation is working. It's saying two things are related if they fit that equation. In fact, if you wanted to graph and see all the ordered pairs that fit this, well, we said 0, 0 works. We're also going to get 1, 1 works. Oops. And 1, -1. Okay, 1, 1, and 1, -1. 2, 2, and 2, -2. Right. Oh, stop it. 3, 3, and 3, -3, and so on. Okay. So notice this is not a function, right? It fails the vertical line test if you want to think of it that way. Relations don't have to be functions. They can, but they don't have to be. But all these dots are elements of our set T, okay? And this would go off to infinity. All right, let's look at another example. So some relations are super well known to where we don't even use a letter for it, we have a symbol for it. So an example of that would be x less than y, right? So instead of saying x is related to y if and only if x is less than y, our symbol is already in relation form. I'm saying, okay, x is related to y, but you know what that less than symbol means. So examples of relations that work with this, and again, this is notation you're used to, you've seen years and years and years, would be something like -3 less than pi, right? I guess I should specify. Let's let our universe be the real numbers squared, so r cross r. So we have then something like square root of 2 less than 100, right? Those are example ordered pairs. If I wanted to graph, just to get a feel for all the ordered pairs that this applies to, okay, we would have everything above the line y equals x, because that's where x is less than y. So everything up here. Okay, so you thought example 1 had infinitely many points. Well, example 2 were uncountably many points. That's a lot of points. Okay. Example 3, this is a super well-known relation, super simple. X equals y, right? And so this, again, let's be in the real numbers. You're used to stuff, right? So pi equals pi. We could get clever, and I don't know, say something like 2/4 equals 1/2, but those are the same number, right? I just represented it in different forms. Okay, so example 3, all the ordered pairs that fit that are just going to be all the ordered pairs on the line x equals y. Okay, so those infinitely many points. Still uncountably many, it just looks like less than example 2. All right, but these, you know, are kind of mathematical equations thinking about, but we don't have to have equation or inequality, okay, to be a relation. So let me give you a super simple example, but not very useful. So let's let our universe, so that'll be set capital X, just be the numbers 1, 2, 3, 4, and 5. Then let's let our relation R be this set of ordered pairs. I don't know, let's take 1, 2, 1, 3, 2, 4, 4, 2, and 5, 5. Why not? That is still an example of a relation. Again, in the grand scheme of things, it's probably not going to be super useful, but it's a set of ordered pairs. So we could say from that, 1 is related to 2, right? 1 is related to 3. 2 is related to 4. 4 is related to 2. 5 is related to itself. Okay, so those are some examples of relations. What we want to do now is look at some terms that apply to relations and see which of these examples fit that. So the first term we want to look at is called reflexive. Okay, so here we go. A relation R on A, so remember that means it's going from A to A. That second set is the same as the first set. Okay. Is reflexive if and only if, right, because it's a definition, for every lowercase a and capital A, lowercase a is related to lowercase a, i.e. itself. So reflexive means everything is related to itself. All right, so let's think back to our examples. So let's take that very first intuitive one we did, the sisters example. Okay, what would I need to ask myself to see if it's reflexive? I need to ask, is X related to X? And this has to be true for arbitrary X, arbitrary people. Well, what's that mean in the case of this? Okay, X, S, X, that's tongue twister. That means X is their own sister. Well, that doesn't make sense. Okay. You can't be your own sister. It's kind of implied in the word that you're separate people. So that is not true. So we would say S is not reflexive. Same thing goes with the mother example. You're not your own mother. Well, we'll say biologically, okay, you could raise yourself, but biologically you're not your own mother, so not reflexive. Let's then, though, look at our T. So we had said in example 1, X, T, Y, if and only if X equals the absolute value of Y. Let's see if this is reflexive. So, is something going to be related to itself? Well, I want X related to X, but that's only going to happen if X equals the absolute value of itself. You say, well, not quite. If X is positive, I'm good, right? But this only works if X is positive. Well, or 0. So an example showing this is not reflexive would be -3. -3 is not related to -3 because that would mean that -3 equals the absolute value of -3, which is not true. So T is not reflexive. All right, well, we still got hope. Let's keep trying with our others. So what about my X less than Y example? Well, you can probably tell right away this is not going to be reflexive because x less than x is not true. So still not reflexive, but the next one's going to work. Okay, our next one was x equals y, and x equals x is definitely true. So this relation is reflexive because that's true for every single possible x. All right, now let's think about r that we made up. So if you look at that relation r we made up, it did have 5 in it. It did have 5 related to 5. That was okay. But it was missing all the others. It did not have 1 related to 1, did not have 2 related to 2, did not have 3 related to 3, did not have 4 related to 4. So that means it is not reflexive. Remember, the definition of reflexive said for every x, or for every a. So here I only got it working for 1, not all 5. All right, so that's reflexive. So hopefully that makes sense. Reflexive means every element is related to itself. Okay. Next idea we want to look at is called symmetric. All right. So here we go. A relation R on A is symmetric if and only if, because it's a definition. Okay, so here's what it takes to be symmetric. It's actually an implication. So we have x, r, y implies y, r, x. So basically, symmetric means you can switch the order and it's still a true statement. Okay? Best way to look at this is with our examples. So let's start with the sister example. XSY means x and y are sisters. But that's no different than saying y and x are sisters. But if y and x are sisters, then y is related to x. So the sisters relation actually is symmetric. If x and y are sisters, then y and x are sisters. So that one is symmetric. Whereas the mother relation is not going to be symmetric. We said that earlier, that the order really matters, right? If x, m, y, that means x is y's mother. I cannot then make the jump. There's no way to make the jump that y is x's mother. So I can't switch the order. So this is not symmetric. All right, let's look at our actual mathematical examples. So t. So x is related to y by t. That meant x equals the absolute value of y. So if I want to try to get symmetric, that means I would need to try to get y equals absolute value of x. But that should look funny to you, right? You say, I don't think I can make that jump. So maybe we can find a counter example. So 3, we said, is related to negative 3, because 3 is the absolute value of negative 3. But we also said negative 3 can't be related to itself, but it also can't be related to 3, because -3 related to 3 would mean -3 equals the absolute value of 3, and we know that's not true. So this is not symmetric. I found a counterexample. I found a specific point that was in T, but his mirror image, you could say, his flipped, is not in T. Okay, got a few more to look at. What about x less than y? Well, hopefully you can look at that and say there's no way that's going to imply y is less than x, right? That makes no sense. I can find a counterexample. Shoot, anything we want. 0 is less than 1, but 1 is not less than 0. So I can't switch the order. So again, we're getting not symmetric. I guess I can write that in here. Not symmetric. Not symmetric. All right. But let's look at then our next example was the equals. X equals y. That does imply y equals x. We know that the equal sign order doesn't matter. If both sides are the same, then both sides are the same. So this one actually is symmetric. Okay, last one leaves that R we looked at, where we just listed 5 different ordered pairs. So if you look in it, it does have 2, 4, and it has 4, 2, so that's good. That shows a little bit of symmetry. Technically it has 5, 5, and then if you flip the order, you still get 5, 5, so that's okay. But the other 2 elements don't work. It has 1, 2, but it does not have 2, 1. So that's all I needed, really, was that bit right there. Ruins it to make it not symmetric. Same thing if you take the second element. It has 1, 3, but not 3, 1. Not symmetric. So again, symmetric means if you have an ordered pair, his reverse has to be there. Okay. All right. The last major word we need is transitive. And you see this word a lot in upper level math. So a relation R is transitive. Well, relation R on A, we should say. It's transitive. If and only if. Again, we are going to get a conditional. Okay, so I need 2 things to happen. I need to have x related to y and y related to x, or z, sorry. The key is that this first and last match. That's what transitivity relies on. If I have that first and last matching in that way, that implies I get x related to z. It's kind of like you collapse the middle down to disappear and just leave you with the outside. Okay. So I'm going to jump to the most obvious one for this, then we'll go back, but I'm going to do the examples a little out of order because the best example and easiest to see, I think, of transitivity is less than. So we're going to jump to the x less than y. All right. So we're going to check for transitivity. So I need to assume x is less than y and y is less than z, right? That fits my hypothesis of my implication. Okay, so I'm assuming x is less than y and y is less than z. But think about it. If x is smaller than y and y is smaller than z, okay, this means x is less than z. Okay, so we do get transitivity. Okay, if x is smaller than y and y is smaller than z, I can combine them and collapse the middle to just get x less than z. That's what we mean by transitivity. All right, and we can just kind of quickly go through the others. Let's say x and y are sisters and y and z are sisters. I know there's some crazy family relations out there. So let's say that by sisters we mean they have the same two parents. Okay, so that we don't get crazy issues. This is why we stick to math terms and not English terms, because definitions get funky and stuff. But if x and y are sisters and y and z are sisters, we can then, by the strict definition of sisters, say x and z are sisters. Because if x and y have the same parents and are girls, then y and z have the same parents and are girls, then x and z have the same parents and are girls. So that's a very, very strict definition of sisters we're going with, not real world definition. Okay, so x and z are sisters. So that would be transitive. But if you think about the mother relation, if x is y's mother and y is z's mother, that does not imply that x is z's mother, right? In fact, x is going to be z's grandmother. So this is a no. This one's not transitive. I'm going to start abbreviating. Okay. Let's see, so we did that one. Now we're on t. So let's assume x is related to y via t, y is related to z via t. We say, wait, what did t mean? That would mean x equals the absolute value of y, and that means y equals the absolute value of z. All right, so I see a problem already with trying to get x equal to the absolute value of z. What if y is negative? No, that's not going to happen. Okay, so if y was negative, I'd have an issue because this wouldn't be well defined. But we're assuming y is related to z. So that means y has to be positive. The only way y can be related to z with this equation is if y is positive. So if y is positive, so we can write that. This implies y is greater than or equal to 0. So I should be saying non-negative. All right. So then the absolute value of y equals y. All right, so now we're ready. So x is going to equal, well, we said absolute value of y, but that's the same thing as y, which is the same thing as absolute value of z. So we actually do get x related to z, because I need x equal to absolute value of z, which I have. So this one actually does work. It actually is transitive. All right. So notice here with transitive, with this example, I do have things like 3, well, let me write it in the other notation, 3 related to negative 3, but I'm never going to have a negative first. So I'm never going to get negative 3 related to something. So I don't have to worry about transitive when it ends in a negative 3, because I'll never have a matching starting negative 3. The only time I'll get a match is if that second one is positive. Then I could have something like this. So 3 is related to itself and 3 is related to negative 3, which I can collapse that down to get 3 related to -3 by collapsing away the middle. Okay, so transitivity does work on that one. Okay, let's see, that leaves x equals y. Well, this one's kind of obvious. If x equals y and y equals z, then duh, x equals z. Okay, yes, that's transitive. Now let's look at our relation R that we just made up a bunch of random ordered pairs. So we said, for example, 1, 2 is in there, so 1's related to 2, and we said 2 is related to 4. According to transitivity, I would need to be able to collapse that down, collapse the middle, and get 1 related to 4. But if you look back, that is not one of our ordered pairs. Okay, so this is not transitive. So in order to show it's not transitive, you only need one spot that fails to be transitive. In order to show it is transitive, you need to take arbitrary X, Y, Z, A, B, C, whatever you're calling them, and show it works. Okay. All right, so that's reflexive, symmetric, and transitive. All these combine to give me something called an equivalence relation, but I'm going to go ahead and split this into 2 videos. So the next video, we're going to look at what do we mean by equivalence relation. We're going to look at some more intricate relations and do some formal proofs on all this material.